How can we communicate how an object moves to someone who does not see the motion? In this video, we will investigate common terminology and motion graphs used to describe motion in one direction. This race car is moving around the track. At any point, we can describe its motion, how far it has moved, how fast is it going, and how quickly it is slowing down or speeding up. Motion is a change in position over time. We describe motion using terms such as distance and displacement, speed and velocity, and acceleration. Kinematics is the science of describing the motion of objects using words, diagrams, numbers, graphs, and equations. Distance and displacement are related, but we use a variety of different measures of motion. Distance is how far an object moves. It is the amount that your odometer changes as you drive your car. It doesn't matter which direction you drive or how many turns you make, the odometer just measures how far the car has traveled. Displacement, however, is the distance an object has moved from the starting position. It doesn't matter how the object gets to a certain position, the displacement is how far, in a straight line, and in what direction that object has moved from its starting point. In the case of the race car moving around a track, the distance the car has traveled is represented by the length of the blue curve that traces its position. The displacement of the car at any instance is represented by the green arrow. The length of the arrow is the distance from the starting position to the position of the car. The arrowhead indicates the direction from the starting position to the car at that instant. Let's illustrate the difference between distance and displacement with a person setting a volleyball straight up in the air and catching it when it falls. At the beginning of the motion, the ball is stationary. Before the ball is thrown, the distance the ball has traveled and the displacement of the ball are both zero. When the volleyball player sets the ball moves straight up vertically. At first, the magnitude of the distance and displacement are the same. However, the displacement also has a direction associated with it, up, which is indicated by the positive value. Distance does not have a direction associated with it. Again, the magnitude of the distance and displacement are the same as the ball continues to move up. Now the ball is at the top of its motion path and begins its descent. The distance the ball has traveled is 10.5 feet, and the displacement is also 10.5 feet up, since the distance between the starting position and the position of the ball is 10.5 feet and still in a positive direction. Now the distance the ball has traveled is the 10.5 feet to the top of the path, plus the 4.5 feet down, a total of 15 feet. However, the displacement is only 6 feet, since the distance between the starting position and the current position is 6 feet. The direction is still positive, up, since the ball is above the starting position. Once the ball returns to the starting position, it has traveled a distance of 21 feet, 10.5 feet up and 10.5 feet back. What is the displacement here? The displacement is zero because the ball is at the starting position. If the ball falls below the starting position and travels an additional 3 feet down, the distance the ball travels is 24 feet. What is the displacement when the ball is in this position? The displacement of the ball in this position is negative 3 feet, or down 3 feet. The displacement is negative because the position is in the opposite direction that we defined as positive from the starting position. Remember, we defined up as positive. So let's assume that you have a sick friend that lives down your street 1.4 miles from your house. You want to take them a special cupcake to cheer them up. You will ride to the cupcake shop, which is 3.6 miles past your friend's house. Buy a cupcake, or two so you can enjoy the treat with your friend, and then ride to your friend's house. After a short visit, you ride back to your house. In this example, what does the arrow represent? The answer is displacement. The arrow represents the distance and direction of the bike rider from the starting position at your house. Another way to describe motion is the speed at which an object is moving. Speed is the rate of change of distance with respect to time. If you know how far an object has traveled in a given amount of time, you can calculate speed by dividing the total distance by the total time it took to move that distance. Common units for speed are miles per hour or kilometers per hour, and feet per second. Let's assume that a bike rider rode from your house to the cupcake shop in 30 minutes. The total distance from your house to the cupcake shop is 5 miles. The total time for the ride is 30 minutes. If we performed this calculation, we would end up with 0.16 miles per minute. But I don't have a good sense of how fast that is. So let's convert to something more familiar, miles per hour. To make this conversion, we will multiply by a conversion factor of 60 minutes over 1 hour. Now, when we calculate speed using the conversion factor, we get 10 miles per hour. Speed is a scalar quantity. That means it's described by only a number. For instance, 10 miles per hour or 35 feet per second. Distance is also a scalar and can be described by only a magnitude. But displacement is a vector quantity because it is always associated with a direction from the initial position. Displacement is described by a magnitude and a direction. For instance, 10 miles due north or 1.5 feet down. Velocity is also a vector quantity and always has a direction associated with it. Velocity is related to speed, but speed and velocity are not the same thing. When we describe motion using velocity, we must indicate a speed, which is the magnitude of the velocity, and a direction. When an object travels in a straight line, the speed of the object is the magnitude of the velocity. For example, the velocity of the bike rider from your house to the cupcake shop might be 10 miles per hour due east, or the velocity of a volleyball being set might be 3 feet per second upward. A motion graph is a graphical representation of the motion of an object. Generally, the motion is represented by a displacement with respect to time. On a Cartesian coordinate plane, time is typically the independent variable and represented on the x-axis. Displacement is the dependent variable and represented on the y-axis. Let's plot the motion of the bike rider. We'll assume the rider rides at a constant speed during each segment of the trip. At each point you reach, we'll plot the time and displacement on the graph below. When you start at your house, both your time and displacement are at 0. It took the rider 30 minutes to ride to the cupcake shop. It took you 5 minutes to buy the cupcakes. You were in a hurry, so it took you only 15 minutes to ride back to your friend's house. You visited your sick friend for 20 minutes. Then you rode home at a leisurely pace because that cupcake was huge, and it took you 20 minutes to ride home. Let's take a look at the information we can get from a motion graph. What was your displacement 10 minutes after you left your house? We can estimate the displacement at 1.6 miles. What is the displacement 32 minutes after you left your house? We already calculated the speed from your house to the cupcake shop to be 10 miles per hour. How does that relate to the motion graph? Look at the average speed calculation, displacement over time. This is simply the slope of the portion of the graph representing the segment of the trip from your house to the cupcake shop. Slope can be determined by finding the rise over run. In this case, the rise is 5 miles and the run is 30 minutes. That gives an average speed of 10 miles per hour. What was your speed between the cupcake shop and your friend's house? We can calculate the slope of the line during this portion of the graph. After converting to miles per hour, we get negative 14.4 miles per hour. What does the negative sign mean in this context? It means that you are traveling opposite to the direction that we assumed to be positive. Since we assumed east was positive, you are traveling at 14.4 miles per hour west from the cupcake shop to your friend's house. We would say that the speed is 14.4 miles per hour, but if we included the direction, we would consider 14.4 miles per hour west to be an average velocity. Look at the motion graph for the segment of the trip during which you were visiting your friend. What is the slope here? The slope is 0 here. The rise is 0, therefore the slope is 0. So your speed is 0. No big surprise. Engineers and scientists use terms such as distance, displacement, speed, and velocity, and use motion graphs to precisely describe motion. These forms of description will help you represent and imitate the motion of a real phenomenon in your automata.